Hello everyone, my name's Dominic and I'm a postdoc researcher at the University of Bath, and I'll be presenting our paper, Sweating the Details, Emotion Recognition and the Influence of Physical Exertion in Virtual Reality Exergaming. This work is proudly a part of the European Media and Immersion Lab and is done in collaboration with my colleagues at Bath. Exergames have been shown to increase enjoyment, performance and exercise adherence compared with conventional exercise. VR exergames are especially interesting as the immersive virtual environment can distract from uncomfortable aspects of exercise, for example muscle strain or nearing the ventilatory threshold. A really key aspect of exergaming is that users enjoy them, and to improve the experience it would be great to measure how they actually feel, for example to adapt to the game. But how do we do this? Well, we could ask people constantly how their feelings change, or we could look at a user's body and their physiology. So why would we want to do this? Well, certain physiological patterns have been shown in literature to change in response to emotional stimuli, and this is in part due to the autonomic nervous system activating in response to our emotions changing, and ultimately these subtle bodily cues can be measured and used to interpret underlying changes in emotion. But doing this for exergaming poses several difficult challenges. If we're using a number of physiological sensing devices, these are typically highly susceptible to noise, and in physical exercise there is a lot of noise. People are moving, sweating, their cardiovascular system is working hard, and their body is generally under strain. Typically, emotion recognition experiments aim to reduce all of this kind of noise, but these sterile environments are not where exergames are played or where emotion recognition technology will be deployed. So, is it still possible to infer emotional change from physiology even while engaging in a high-intensity VR exergame? And we specifically wanted to address 4 research questions. RQ1. How can we manipulate affect in a VR exergame? So can we create exergame environments that can still elicit and target particular emotions despite a user being under intense exercise? RQ2. How well do physiological factors predict affect during VR exergaming? So what happens to these measures under intense exercise, and are they still robust estimators? RQ3. How can environmental and interpersonal factors influencing physiological sensor data be accounted for? So what sort of techniques can we employ to tease apart the effects of exercise and emotion on physiology? And can VR technology be leveraged for this? And RQ4, what is the relationship between physical exertion and emotion during VR exergaming? So the effects of physical exertion on emotion are well understood, but is this the same for VR exergaming? For brevity, I will only discuss RQ2 and 3 in detail, but will provide the takeaways for all research questions. So to answer these research questions, we designed 4 different emotion-inducing exergame environments: stress, happy, sad, and calm. And we specifically picked these emotions as they each sit centrally in something called the circumplex model of emotion, which is a conceptual model developed by James Russell in the 80s. It's a 2-dimensional model, and it's made up of valence dimension, which is a pleasure scale, and an arousal dimension, so how alert or activated someone feels. And within these quadrants sit categorical emotions like happy and sad. And so we got our virtual environments to fit within this model, and we surveyed a large amount of literature on emotion elicitation in VR, and emotional game design to develop these environments. But please refer to the paper for the specific design choices. But here is a closer look at 2 of these environments. So after we designed these environments, we wanted to start collecting some data, and we chose to focus on 10 physiological measures that have been shown to bear linear relationships with certain emotions or affects in literature. And so we also surveyed the literature on this to produce hypothesized relationships which we would expect to see between the physiological measures and 10 popular measures of affect. We then applied 3 different levels of increasing data cleaning, which I'll briefly mention here, but please refer to the paper for more detail. So we have the raw level, this is just what the sensors provide us. Then we have the environmental cleaning level, so we're removing noise artifacts created by the exercise and also created by the virtual environment. And then we have the personalized cleaning level. So everybody's physiology and baseline emotions are very different. So we use a statistical technique to remove interpersonal differences in both the physiology and affect ratings. But the goal here is to see what is the effect on estimation power with increased data cleaning. So onto the study itself, we recruited 72 participants and the procedure looked a little bit like this. We had 3 exercise intensity levels, low, medium and high, and participants were first loaded into a neutral environment in which they began an initial warm-up to get them in the right heart rate range, and then they were administered the emotional exergame for 60 seconds. After which they are taken back into the neutral environment to engage in a cool down, and this is also where we take ground truth measures of affect. And then they repeat this process for each of the 4 virtual environments, and this whole procedure is repeated for each of the 3 exercise intensity levels. So, onto the analysis and results. For RQ1, we had 4 hypotheses families around how each VE should elicit and target particular emotions, and we ended up accepting these 4 hypotheses families, and emotion elicitation was overwhelmingly robust to the effects of exercise level. But there were 2 exceptions worth mentioning that came up in our extended analysis, and this is to do with the happy and calm VEs eliciting similar happiness and calmness, but this was only at the high intensity level as they were accepted at low and medium intensity. And we think this is due to the similar and non-exclusive nature of calmness and happiness, which seemingly have some interaction with intense exercise, perhaps becoming more blended. But ultimately, we accept 94 of the total 96 hypotheses that we had. On to RQ2, we use multi-level linear regression models to test the relationship between physiological measures and emotion variables. And this table shows the significant linear predictors, and whether they are red or green shows whether they are negatively or positively correlated with the associated affect variable. And so we can see that pupil dilation measures, PDL and PDR, are universally significant predictors of affect during VR exergaming, and power and smile are also often significant. And skin conductance level, SCL, is significant occasionally, mainly for arousal and stress. We can also look to the coefficient of determination R², which describes the model fit, and we consider anything above a 0.1 to be an adequate model. But in this case, we can look at our happy, sad and bored models and see that they fall below this. But the rest of the models are adequate. So taking a look at this in more detail, specifically the models for these 4 affect variables, the bold numbers are the hypothesized predictors, and for the most part these are accepted, but there are some notable exceptions that were rejected. Particularly skin conductance response for arousal and stress, and heart rate variability for valence. These measures are used a lot in literature, but in the context of VR exergaming, these predictors simply weren't significant and simply aren't good enough. Moving on to RQ3 then, onto data cleaning, let's take these 4 same adequate regression models and look a bit more under the hood at the 3 different cleaning levels. Raw, environmental cleaning, and personalized cleaning, which you can see on the left there. And this table is quite dense, so let's just look at 2 of these models in more detail. So what we're looking at here when comparing the cleaning levels is a few different things. First, we're looking at whether the model is robust to increased exercise intensity, i.e. do we only need 1 model or do we need 3? In both fear and arousal, as you can see, the more cleaning you do, the more robust the model is. We also look at the coefficient of determination, R², and this is describing the adequacy of the model, and in both cases, as you increase the cleaning, the R² coefficient also increases. And we're also looking at the standardized coefficients of each physiological measure and whether they're significant. We should also look to see if assumptions of linear regression are violated, such as fear pupil dilation level violates linearity right until the personalized level, at which point it is no longer violated. And finally, we should also look to see if there are changes in the polarity of significant predictors. So for skin conductance level for arousal, at the raw level, it is the completely wrong correlation, because in literature, SEL is strongly positively correlated, so we can know that the raw cleaning level is showing the wrong correlation. But with the appropriate cleaning, we see a variable is sensible. I will very briefly mention the main outcomes of RQ4, and that was that physical exertion can be used as an estimator of emotions, but just using exertion alone often yields inadequate regression models, with the notable exception of arousal, which lines up quite nicely with literature, as exercise is often used to induce arousal in experiments. We also looked at people's intrinsic motivation at each exercise intensity level, and we saw a clear and significant trend that as exercise intensity level increases, interest, enjoyment, and perceived competence decreases, and the pressure and felt tension increases. For the rest of the detailed results, please refer to the main paper. So let's discuss what these findings mean for our research questions. For RQ1, we were able to construct VEs that were robust in the emotion elicitation, and so exergame designers should consider game mechanics, environment aesthetics, and sound design. Our elicited sadness was relatively low, and so other methods could be used to induce it, such as narrative devices or social situations created through non-playable characters. We did not target boredom explicitly, but this is an important emotion for us to detect in an exergame, so other methods could be used to induce it, such as linear gameplay or lacking challenge or visual variety. For RQ2, our results confirm many physiological measures that have been reported in emotion recognition literature, and we have produced 7 adequate models. We've also observed that pupil dilation, smile, and power are strong predictors, and were mostly in agreement with literature. However, we rejected some popular physiological measures, particularly heart rate variability, skin conductance response, but skin conductance level was sometimes useful for estimating arousal and stress. We had 3 inadequate models, which either could indicate that the relationship with emotion is nonlinear, or other measures could be considered. For data cleaning, the relationship between cleaning and model adequacy couldn't be clearer. We see a trend of increased significant predictors and an increased R-squared value, and decreased violations of assumptions as you go up these cleaning levels. Minimal data cleaning also runs the risks of models overfitting to the stimuli, for example, one environment being brighter than another when measuring pupil dilation. So everyone should really consider what the physiological byproducts of their stimuli and the activity are. And of course, there is always room for additional cleaning measures, especially for our weaker estimators. Physical activity of course creates noise, but it also influences people's emotions. Our results support the known effects of exercise observed in literature, but the regression models had weak coefficients and were mostly inadequate, which further supports this notion that exergames can distract from those uncomfortable sensations of exercise. Aside from those discussion points, we also offer concrete guidelines for those interested in doing affect recognition in VR exergames. There's lots of avenues for future work with this project, but I'll briefly mention one. Because we developed our models in such a physiologically noisy context, these models and techniques have high applicability to other equally noisy contexts where there's any sort of physical activity or exertion involved. And we hope to already help other researchers get started on future work. We have concrete guidelines in the paper for those interested in doing emotion recognition in VR exergaming, and we also have a bunch of available artifacts for people to use. We've got an extended analysis report and aggregated dataset in supplementary material. We've got a full raw dataset which is available on our research data archive for people to already start tinkering with, and we have made all of our virtual environments available on GitHub, and the physiological data collection and cleaning software is available on request. And with that, I thank you for your attention.